but wherever this arm goes with it. And then on top of that, this arm can go from 0 degrees to 90-ish, maybe a little more. So you've got these stacked transformations. Wherever the body translates to, this and this need to inherit that translation. And then after that, you specify a rotation on this arm about that joint. And to rotate about anything that's not the origin, you have to translate that point to the origin, and then rotate, and then translate back again. So it's 3 transformations to get a rotation about a point that's not already at the origin. And then this one will inherit that transformation, and then on top of that, you can rotate this one. So you end up stacking these transformations on top of each other. So we talked about GL push matrix. That says save everything on the open GL current transformation matrix so that I can put it back later. And then you do all the GL scales, rotates, and translates. For the most main part of it, the body. And then you could GL push the matrix again, save it at that point. Let's see, wanted to do 2 arms. Save where the body was, and then push the matrix for this rotation. So that will save it. And then upper right arm. Then you do a rotation, which again, to do one rotation, it's a GL translate this point to the origin, followed by a GL rotate, followed by a GL translate it back again. I forgot, right here, you draw the torso. So all of the vertices that are part of the torso get drawn there. And then after you've set up the matrix for the upper arm, you draw the upper arm. And again, you always draw the upper arm in its default position. But because you do this first, it'll get drawn anywhere between here and all the way up to there. And then you do the forearm. Again, you do I'll just say the matrix operations, matrix ops for the upper arm, the lower arm, and then you draw the lower arm. You know, depending on how much detail this is, if you're doing it for a video game, there might be thousands of polygons in the character's main torso, and then hundreds of polygons here and hundreds of triangles here. And you might hierarchically go a long ways out, down to the wrist, down to the finger, and even the lower fingers, if it's got a lot of detail. At each level, adding another layer of matrix, 1 second. And then as you roll back out, I'm done drawing pushing the matrix for this finger, drawing it, then you would GL pop matrix to roll back off of this finger, and then you would push the matrix for the rotation of that finger, draw it, and then pop it, and then push the matrix for the rotation of that finger, and then pop it. And then after you've drawn all of those, you would pop the rotations or the matrix operations you did for the wrist. And then you would pop whatever ones you did for the lower arm, and then pop the upper arm. And then you would push the ones for the left arm. And you basically just walk all the way up and down the skeleton of the person you're modeling.
That's low-key.
It's what?
That's gnarly low-key.
Yeah, that's the way it's done. I've worked at a game company, and I can show you, well, I can't because we have no video, but I have the skeleton of characters that we used, and it's pretty cool. What were you gonna say, Jessica?
So I had two questions. One is, can we make this a recursive function then? Yeah, so the torso would likely own the two upper arms, and so drawing the torso would draw its own body, and then it would have a pointer, or maybe it wouldn't be a pointer, maybe it would just have two arms as part of itself. And then it would say, draw my right arm, draw my left arm, and then they would in turn say, draw, when they're done drawing them, they would say, draw the things hanging off of me.
It's like draw a child.
Yeah.
Everything's called
And then the hand would say, after drawing the hand, draw each of my fingers in turn, and then, so we have very much hierarchically drawn.
Okay, and my second question was, why do you do GL translate and then again after you rotate?
Because
you translate to the origin, rotate, and then translate back.
yeah, that's what you need to do.
Why?
Because if you don't, you leave the world shifted over. If this is the world, and this is 0, 0, and I want to spin the world about this point right here, like that, 30 degrees about this point, there isn't a command that I can say to spin about 5 over and 3 up. So I basically shift the whole world -5, -3. That's everything, the whole world. And then I spin the whole world about the origin, and then I move the world back here because I want him right there. That's where the character is, and that's where I want him. But, so when we're done, you know, he starts like that, and when we're done, if I spin him 90 degrees, he's right there looking like that. But if I just moved him to the origin, he would be right there. And if I moved him to the origin and spinned him, then he would be right there. But I have to move him to the origin, spin him, and move him back again to get him where he started.
Okay.
Yes?
So the reason you have to do all this in such a weird way is because it's happening in the graphics card, right?
Yes, and that's where I'm going.
Okay.
Because I'm trying to make the point that by the time you get to the fingers out here, there might be 30 different commands here. Translate, scales, rotates, and some other ones too. And every one of these represents a matrix. And I'll go into what a translate matrix looks like versus what a rotate matrix looks like versus what a scale matrix looks like. But they're all 4x4 matrices. And in the end, by the time I'm drawing this finger, there's a collection of all the matrices of everybody on top of it hierarchically. And
the vertices of the finger has an X, Y, Z, and we put a 1 there. So let's say there's 30 vertices that are connected into triangles representing the finger. All 30 of those have to get multiplied by all 25 of these matrices, except they don't, because matrices are associative, which means instead of multiplying the finger by this one, and then by this one, and then by this one, OpenGL actually doesn't keep track of all these. It multiplies them all as you go into one matrix called the current transformation matrix, the CTM for short. OpenGL keeps track of two matrices, the current transformation matrix. Actually, they call it the model view matrix. The model view matrix and the projection matrix. When you call inside reshape, when you call GL ortho to set up an orthographic projection, that goes here. It splats 3D down to 2D. Or if you call GLU perspective, was the other one we did, then that goes here. All of these commands, translate, scale, and everything else, when you call GL load identity, then it fills this one with the identity matrix, which is ones down the diagonal and 0 everywhere else. That's what calling GL load identity does. You've seen that in their code. And if you multiply any X, Y, Z 1 by the identity matrix, you get the same thing back out again. So we usually start every frame by loading the identity matrix into the model view. So in the end, what we want is to multiply all 30 vertices of the finger by all of these, and then multiply it by the projection matrix. And then we get final points back out. And these are 2D points in screen coordinates. But so every time you do one of these calls, OpenGL does a left multiply by this matrix. So that's why we have to do them in reverse order, because internally it needs this one to be next to this one. And so it left multiplies them in, which is why they have to be fed to them backwards. But in the end, because it's associative, you don't have to multiply this by this first and then by that by that. You basically multiply all 30 of these together into one matrix first. And then you take your geometry, and 30 is not very many. If it's the torso, it might be 10,000 vertices on a really well-defined character. And then it only has to multiply the 10,000 vertices of the torso by one 4x4 matrix, and it does it in GPU hardware, so it's super fast. And it can just rip through a ton of vertices, gets them in 2D, and then it remembers how they were connected in 3D, and it reconnects the 2D vertices and pixel coordinates into triangles on the other side. Yep.
So the multiplication of the 25 matrices produces the one identity matrix?
No, it produces, it starts as the identity matrix when you call GL load identity.
Oh, okay.
But then, when you start calling GL rotate and GL translate, every time you call one of those, it multiplies it into this.
Okay.
So this collects all of the rotate, scale, and translate commands. And then when you've got them all connected, and then you start saying, actually draw the finger, it only multiplies it by this one matrix and this one matrix. These are the only two that OpenGL actually needs to store. Everything else gets multiplied into it. Okay? Is that making a little bit of sense? Probably didn't explain it very well because I'm a little off my game from the stupid projector. So if you call GL translate and say, I want to move everything over by 3 and 5 and -2, what kind of a matrix does OpenGL make for you behind the scenes and multiply into that? Always makes a 4x4 matrix. And this is what it does. 1, 1, 1. 1, 3, 5, -2. And all the rest are zeros. So given any and all x, y, z points, if you multiply a point by a matrix, I don't know if you remember how to do this, but to get the answer, you do the dot, basically the dot product of this column times this row goes right here. So 1 times x plus 0 times y plus 0 times z plus 3 times 1. That ends up with x plus 3. 0 times x plus y plus nothing plus 5. Y plus 5. And then when I do this times this row, it's no x's, no y's, 1z minus 2. And here I get 0 x's, 0 y's, 0 z's, and 1. So you can see that if OpenGL builds this matrix for a translate command, it will cause any point x, y, z to be pushed over to whatever, however we said we wanted to translate it.
So if we're using 3D points, what's the point of using a 4x4 identity matrix instead of a 3x3?
Because, it's a good question. Because if you try to make a 3x3 matrix that would do this translate that we just did, you couldn't.
Yeah, your negative
There doesn't
2
exist one.
Your -2 would be where the 1 has to be.
Yep.
But why does the 1 have to be there?
In order for it to remain an identity matrix.
If you tried to do this with a 3x1 and a 3x3, there is not such a matrix that will give you the correct answer for translating.
So
In other words, you still have to have the pre-existing x, y, and z components And so you need a partial identity matrix in order to carry over those X, Y, and Z components. And if you did it with a three-way matrix rather than a four-way matrix, that existing Z component would get overridden with your current Z component when you want to enter into the matrix.
Sure. It can't be done.
The first three columns represent X, Y, and Z. Is that, I'm confused about the, so,
Here,
yeah.
I'm just showing you what kind of a 4x4 matrix you need to multiply a point by to get it translated by a specified amount. And I'm kind of assuming here you guys are already familiar with matrices and how to multiply them. So assuming you know how to multiply a 4x1 by a 4x4, this is the trick for making a 4x4 matrix that will translate any XYZ point by these three amounts. Now I'm going to show you the trick for given any XYZ point, how to scale it by, I don't know, 2, 3, 4, and X, Y, and Z. You make this 4x4 matrix. Across the diagonal, 2, 3, 4, and 1. Everything else is zeros. That's the matrix that OpenGL will make for you and multiply into here for you when you say GL scale. Again, it's all matrices behind the scenes. And it all goes into here, behind the scenes. For GL rotate, if you want to rotate about the I'll just say the x-axis. Now let's do the z-axis. Rotate about z theta degrees. Then you put sine, cosine of theta.
It does it in degrees though, it doesn't do it in radians.
Well, these thetas, you give the GL command degrees,
Okay.
and here it needs to be radians when you're taking, when OpenGL takes the cosine of it, or if you make your own matrix. Sine theta minus the sine of theta, and then 1 and 1. So the upper left corner is the cosine theta and the sine of theta, and it's 1s down the diagonal and 0 everywhere else. Notice that if you say rotate 0, cosine of 0 is 1s, and sine of 0 is 0. So if you say rotate 0, you get 1s in the diagonal, which doesn't do anything. So that'll rotate about z. And I could show you how to rotate about x and y as well. You just shift these. And then to rotate about some other axis is significantly harder and not something I have memorized, but you can basically rotate about any axis by combining rotates about z's, x's, and y's. You can build anything else. Anyway, it's 2:47, and I think a lot of you want to pass off your 3D maze, so let's call it a day. Yes?
Is the first entry, in that first row, is it cosine times the sine of theta, or is the sine in the middle?
This is, the top left corner is cosine theta, that's all.
And then the next,
And then 1 over is the sine of theta. And then it goes 0, 0. And then minus the sine of theta, cosine theta, 0, 0. And then 0, 0, 1, 0, 0, 0, 0, 1.
thank you.
So if you wanted to build your own rotation about the z-axis, that will be very helpful. If you just were doing your own project and you wanted to do your own rotation. Take the sine and cosine of theta in advance if you want to push a lot of points through it. Okay. I'm going to sit right here and let you guys come up if that's okay.
That looks exactly how it should be.